What's up? My name is Nicholas Bramall. This is Lab 3 Lab Report. The purpose of this lab is to better understand how gravity affects objects in motion in different situations, one being a two-body system and two being a three-body system. And we found that by adding another body into the system, it makes it drastically harder to predict the smallest object's motion, or even all of them. In the problem, we had the star being the system and the black hole being the surroundings in part 1, and part 2, the ship was the system and the two planets or the moon was the surroundings, because that's what we were concerned with. And the answers we eventually came up with was 1.93 E31 for the mass of the black hole, and the velocity was 2.54 E4 for the x and y components of velocity. So let's get this! Woohoo! Here are some equations we need. First up, F-grav. This is what we use to find the mass of the black hole by finding the F-net, which is going to be just F-grav. And so when we set the two equal to each other, we can solve for M1. And then over here on the right, we have the F-net parallel and the F-net perpendicular components, which are used to find F-net and also account for its changing velocity. We have to find the changing velocity, plug that into these, get F-net from that, and plug that into here. Boom, we got that. All right, methodology. So part 1 is essentially, like I said, we got a star revolving around a black hole, and then using the change in velocity, we calculate the change in momentum, and then using that, we can find the F-net, and then set that equal to F-grav, find the mass. Now, due to the fact that it's not circular motion, uniform circular motion, the velocity, change in velocity is not going to be constant, and so the mass is gonna like vary kind of each cycle, but it's gonna be reasonably close, and so the average is gonna be very close. It's a good approximation. Now, part 2, there's 3 bodies influencing each other. One is stationary, which is the main planet. And the goal was to find a velocity where the ship, the smallest mass, is bound and is being and the force is exerting from both of them onto the ship, but it doesn't crash. And we were hoping for a figure 8, but we did not get one, but there's evidence of influence from both masses. Here's the code from part 1. Over here on the right, we've got the initial conditions, initial positions, mass, constants, all that jazz. Over here on the left, we got the calculations. We got velocity, we got momentum, change in velocity, change in momentum, we got the dp dt, we got the parallel, and we got the perpendicular components down here. And then finally, using that stuff, we were able to get the mass of the black hole right here at the bottom using the change in momentum. And then we printed it out. Alright, you can see here we got the results down here. The change in a little bit due to the changing velocity. However, the average is still very close to what it should be. Now, part 2, we got the initial speed over here of this spaceship. Over here on the left, we got the initial positions and the masses, constants, all that jazz, yum stuff. Now, below it, we got all the equations. We got the force from the planet on the moon, ship on the moon, and then the F-net on the moon, and then suddenly down here, F-net on the ship, and we use that stuff to calculate the velocity, and then finally the position each cycle, and that is how we get this beautiful graph right here. Now, you can see here, it's not a figure 8, which is sad. However, you do see the effect of the planet on the, the moon on the ship, because if it was just the planet, it would just go in a, normal orbit, like in the first part. However, you can see it most clearly here where there's, like, you would clear to do one of these numbers, going in just like the elliptic, but right here, there's a slight curve that goes out, and then it goes way down south, and that's due to the fact that there was a planet right here, quite close, so its force was quite big on it. Next up, we got possible sources of error, and in this lab, there's only really one thing we have control over, and it's the calculations, so that's the only possible source of error. However, the math has been checked over many, many times. The results are kind of what we're expecting, and so we can have confidence that this is not a source of error, and we're good. Now, discussion conclusion. What does it mean? Well, between the F-net and the parallel, in perpendicular components, and also the change in momentum, value-wise, they're the same, but what they represent and what they mean can mean different things. The F-nets we can identify as that's what's causing the change in momentum. However, the change in momentum is how much it's changing. And so the gravity, the force of gravity, is what's causing the change in momentum, and it's changing it by F-net amounts. But the change in momentum is the actual value. It's each time it's changing by this much. and that effect applies similarly to the components as well. Now, what if in part two what if we added in another black hole? Well, the mass from the black hole would dominate; it would suck everything in. But so there would no be equal contribution. It heavily depends on the mass of whatever it is in the distance. Now, once again, the answer for part 1 and part 2 was found to be 1.93 E31 for the mass, and velocity was 2.54 E4 for both x and y components. Thank you very much. Have a good day. Woohoo!